Alright class, today we're going to continue our discussion of derivatives, but with a focus on the chain rule for derivatives. The chain rule tells us what to do if we want to take the derivative of a function that can be written as a function of a function. This may seem a bit esoteric, but it's actually really powerful because it allows us to break complex functions up into much simpler functions that we know how to take the derivative of. We'll also use this chain rule to investigate equal growth rates and to prove a couple of the derivative equations that we used in the last toolbox. But first, we'll review those previous derivative toolboxes. So far, we've covered several different equations that we can use to figure out the derivative of a function that is a combination of other functions. We've covered situations that involve adding or multiplying by a constant. We've covered situations that include addition or subtraction of two functions. We've also covered situations that include multiplying two functions by each other. These rules are all summarized on this slide. First, if you're adding a constant, if f of x equals g of x plus c, then the derivative of f of x is simply the derivative of g of x. This equation also works equally well for subtraction, because subtraction is just addition of a negative number. Next, we've got an equation for when your function is created by adding two other functions together. If x is equal to g of x plus h of x, then the derivative of f of x equals the derivative of g of x plus the derivative of h of x. Next, we have an equation for multiplying by a constant. If f of x equals the constant c times g of x, then the derivative of f of x equals c times the derivative of g of x. And finally, we have an equation that tells us what to do if we need to take the derivative of two functions that are multiplied by each other. If f of x equals g of x times h of x, then the derivative of f of x equals g of x times the derivative of h of x plus h of x times the derivative of g of x. These are all important equations, so don't forget them. But let's move on to a topic that's more applied. Let's talk about the growth rates of a bacterium like E. coli. Bacterial growth responses to temperature can often be described using what's known as a Q10 value. The Q10 value, which is also sometimes referred to as the Q10 temperature coefficient, is a measure of the rate of change of the growth rate of the bacterium as a consequence of increasing the temperature by 10 degrees Celsius. If you measure the growth rate of a bacteria at two different temperatures, you can calculate the Q10 value for that bacteria using the equation Q10 equals the growth rate at temperature 2 divided by the growth rate at temperature 1 raised to a power equal to 10 divided by the difference in the two temperatures at which the bacteria were grown. Another way that we could state the definition of the Q10 temperature coefficient is that it is the proportional increase in growth rate of the bacterium if the temperature goes up by 10 degrees Celsius. For instance, a Q10 value of 2 means that the bacteria's growth rate doubles if the temperature goes up by 10 degrees and quadruples if it goes up by 20 degrees. Similarly, a Q10 value of 3 would mean that the bacteria's growth rate triples if the temperature rises by 10 degrees and goes up by a factor of 9 if the temperature rises 20 degrees. If we know the Q10 for a bacteria, and we know the growth rate at one temperature, which we'll call G1, then we can calculate the growth rate at any other temperature using the equation G2 equals G1 times the Q10 value raised to temperature 2 minus temperature 1 divided by 10 degrees Celsius. If we know the growth rate at 0 degrees Celsius, which we often write as G0, we can compute the growth rate at any temperature using the equation G of T equals G0 times Q10 to the temperature divided by 10. If we graph this equation, we can see how the growth rate varies with temperature. It's an exponential increase. In this instance, I've graphed it with a Q10 value equal to 2. Okay, this sort of information can actually be really useful to us. For instance, let's say there was an outbreak of E. coli on some contaminated romaine lettuce, as happened during the second half of 2019. If you were working for the FDA, your boss might task you with trying to predict how bad this outbreak could be in Tallahassee. Obviously, the growth rate of E. coli is really going to be important to figure out how potentially harmful it might be. And we know that its growth rate is strongly temperature dependent. So if the ambient temperature is warmer, there will be more E. coli growing on the lettuce. Well, we know that temperature varies a lot between winter and summer in Tallahassee. So our first step might be to try to figure out what the temperature is at different times of the year. So we download some historical data about the monthly temperature in Tallahassee. When we look at this data, we see that the temperature, of course, goes up and down every year with the seasons. In the summer, it looks like the temperature is usually about 81 or 82 degrees Fahrenheit, and in the winter, it looks like it is usually about 60 degrees Fahrenheit. Of course, since we're scientists, it looks like it's about 50 degrees Fahrenheit in the winter. Of course, since we're scientists, we need to work in degrees Celsius, not Fahrenheit, so we will use the equation that the degrees Celsius equals the degrees Fahrenheit minus 32 times 5 over 9. So let's plug in our estimate of 82 degrees Celsius, and we'll compute that 81 degrees Celsius equates to 27.2 degrees Celsius. Similarly, if we plug in 51 degrees for our average winter temperature, we find that this equates to 10.6 degrees Celsius in the winter. Alright, armed with this knowledge, let's try to write an equation for the temperature as a function of time. Alright, obviously this looks like one of our sine waves. So what do we know about that sine wave? Well, we know that it should have a period equal to 365 days because it goes up and down once per year. We also know that it should have an amplitude of 8.3 degrees Celsius because that is half of the difference between the average summer temperature and the average winter temperature. So we can write a sine function with this amplitude and period. Temperature equals 8.3 times the sine of 2 pi divided by 365 times d, where d is the time in days. Okay, that's a start, but we know that can't actually be correct because we know that the sine function reaches its lowest point 3/4 of the way through its cycle, rather than near the beginning like our temperature plot does. So let's actually shift the phase of the function. We can shift the phase 100 days later by subtracting 100 from d in the equation. Alright, we're getting closer, but there's still one other thing that's wrong. Remember, the sine function will center around a temperature of 0 and will go down to a value equal to negative the amplitude and will go up to a value equal to the amplitude. Alright, so we need to add something to the function to shift the whole function upwards. And we'll add a value equal to the average temperature throughout the year, which is equal to 18.9 degrees Celsius. Alright, this gives us an equation to estimate temperature throughout the year. Let's plot it to see how well it fits the data. It turns out that it's a pretty good fit. It looks like there's a little bit of a misfit in the fall, in the months of September and October, but for the most part it works really well and is probably good enough for our purposes. So now let's talk about how we actually calculate the growth rate as a function of time. Okay, we know that growth rate is a function of temperature, which we're calling capital T, and we know that temperature is a function of the day of year, which we're calling D. Remembering back to what we learned about functions of functions earlier in this course, we know that if we want to calculate equalized growth rate as a function of time, we should rewrite our equation g of t by stating that g of t of d equals g0 times the q10 value raised to a power of t of d divided by 10. We can then substitute in our equation for t of d into this equation. Alright, we've got an equation for computing the growth rate as a function of time. But what happens if we want to figure out how fast the growth rate might be changing? This could be important if, for instance, we have an outbreak that starts in April and we want to see how much worse it might get in the future as the growth rate of the bacteria keeps changing. Well, we need to compute the derivative of g with respect to d. But that's not something we know how to do yet. We certainly haven't talked about how we compute the derivative of a function that has a sine function inside an exponent. But there's a mathematical trick that can help us solve this problem. So that's what we're going to talk about next. Alright, as we try to learn how to compute that derivative, we're going to use something that's known as the chain rule for derivatives. It's a really important concept from calculus that we actually use a lot. It can be used anytime you have a function that is a composition of other functions. For instance, if we had a function that was the sine of e to the x squared plus 2x. This is a complicated function, but it's really put together out of 3 simpler functions. But before we get to solving a more complicated function like that, let's start off with something much simpler. Let's start off with 2 pretty simple functions that we know how to deal with. We'll write 2 functions. f of t equals 2t squared and g of t equals 5t cubed. Then let's ask the question, what is the derivative of f of g of x? We know that we can find f of g of x by writing f of t and then substituting in g of x instead of t. We could then take the square of 5x cubed, compute this, and just take the derivative of f of x if we wanted to. But let's not do that just yet. Let's try something different. Let's forget that equation for just a moment, and instead let's just write that h of x equals f of g of x, and think about what it really means if we want to take the derivative of h with respect to x. Well, as we look at this equation, let's think about what it would mean if we think about g as just some variable. Don't think of it as a function of x for a minute. Just pretend that it's some variable and forget that it in fact varies as a function of x. Alright, if we think of that as just f of g, then we can compute the derivative of f with respect to g. It'll simply be the same thing as the derivative of f with respect to t if we just think of either of them as variables. The function f is just a simple polynomial, so we can calculate that since the derivative of f with respect to t is equal to 4t, then the derivative of f with respect to g is simply 4g. Alright, that tells us how fast f is changing with respect to g, but we really want to know how fast f is changing with respect to x. So let's go back to thinking about the fact that g is not just some silly little variable. It is itself a function of x. Alright, we know how fast f is changing with respect to g. Next, let's calculate how fast g is changing with respect to x. Well, again, g is a simple polynomial, so we can easily compute the derivative of g with respect to t as 15t squared. So of course the derivative of g with respect to x will also be equal to 15x squared. Alright, let's think about what we've got here. We want to know how fast h changes due to a small change in x. That's the definition of the derivative. This means that we want to know how fast f of g of x changes due to a small change in x. We already know how fast f changes due to a small change in g, and we know how fast g changes as a result of a small change in x. So it makes sense that we could compute how fast f of g of x changes due to a small change in x by simply multiplying how fast f changes with respect to g by how fast g changes with respect to x. Or in other words, dh dx equals df of g of x dx, which is equal to df dg times dg dx. And we already know those equations, so we can just substitute them in, and we'll also see that we don't really want to keep g in this equation, so we'll need to substitute in for it. Alright, once we've plugged in for g of x, we can now just compute that derivative by multiplying everything out, and we'll find that the derivative of h with respect to x is equal to 300x to the fifth. Okay, we've got our answer, but because this was a really simple function, we can actually check it to make sure that it's correct. Remember, before we realized that we could actually compute f of g of x pretty easily, and when we do, we find out that it's really just a simple polynomial. It's equal to 50x to the sixth. And of course, we know how to compute that derivative. It's simply equal to 50 times 6x to the fifth. And of course, that's exactly equal to what we calculated using our other approach, which is referred to as the chain rule. The chain rule is actually really important, so let's take a moment to look at it. Our chain rule tells us that the derivative of f of g of x with respect to x is equal to the derivative of f with respect to g times the derivative of g with respect to x. If you ever have trouble remembering this equation, there's one simple trick that you can use to think about it. You can think of it as if it were a nice simple product of two fractions, in which case dg in the denominator of the first one would cancel out with dg in the numerator of the second one, giving you df dx, or the derivative of f with respect to with respect to x. Nice and easy to remember. Alright, that previous equation that I wrote out was so simple that we were able to calculate it without using the chain rule, which of course is why I chose it, because it allowed us to test the chain rule. But now let's go back to the more complicated equation that I wrote down before. I wrote out that f of x equals the sine of e to the x squared plus 2x. This is an equation for which we really need the chain rule if we want to compute the derivative. So let's see how this will work with this more complicated equation. Let's first off break this up into parts. Well, this function includes a sine function. So let's write a function g of t equals sine of t. This function also includes an exponential. So let's write another term, h of t equals e to the t. And f of x also includes a polynomial. So let's write that j of t equals t squared plus 2t. Now this means that we can write that f of x equals g of h of j of x. We can also write that h of j of x equals e to the x squared plus x. Alright, next let's compute some derivatives. The derivative of sine of t we of course know is cosine of t. The derivative of e to the t is e to the t. And the derivative of 2 squared plus 2t is 2t plus 2. Alright, now let's apply our chain rule. We know that f of x equals g of h of j of x. So here we have a function of a function of a function. So we can write that df dx equals the derivative of g of h of x with respect to x. And our chain rule tells us that this derivative should be equal to the derivative of g with respect to h times the derivative of h with respect to j times the derivative of j with respect to x. And we can take the derivatives that we already calculated and plug them into this equation, keeping in mind that our derivative is dg dh instead of dg dt, and dh dj instead of dh dt. So this gives us the derivative of f with respect to x equals the cosine of h times e to the j times 2x plus 2. Alright, next we'll notice that we still have h of j of x and j of x in that equation. Well, we know what h of j of x and j of x are actually equal to, so we can substitute in for those, and we find that the derivative of f with respect to x equals cosine of e to the x squared plus 2x times e to the x squared plus 2x times 2x plus 2. Alright, let's clean things up a bit, and then let's actually graph this to see if it works. In the top graph, I have our function f of x, and the animation is showing you the slope of the tangent line like normal. On the bottom graph, the thin blue line shows the derivative that we calculated, cosine of e to the x squared plus 2x times e to the x squared plus 2x times 2x plus 2. And the line that you see moving across it with the pink dot is the derivative calculated using our geometric definition of the derivative, which is the slope of the line tangent to the function f of x. You'll notice as you watch this that the function we calculated directly using the chain rule perfectly matches the derivative determined using the slope of the tangent line. You'll also note that although the amplitude of the function f of x never changes and is always between -1 and 1, the amplitude of the derivative grows substantially over time. This should not be surprising to you, since the equation that we wrote for the derivative multiplies the cosine function by an exponent. It also makes intuitive sense because as the period of the wave function gets shorter and shorter, the function is going up and down by the same amount, but over a shorter and shorter period of time, which means that the amplitude of the derivative has to be getting larger. You should also notice that the derivative has to be getting larger. And anytime the slope of that line gets really high. In addition, the derivative is still going to be 0 every time the function f of x reaches a maximum or a minimum and flattens out. Alright, now that we've learned to use the chain rule, let's get back to that bad lettuce. We know that we have our growth rate g of t of d, which is a function of temperature, which in turn is a function of time. So the chain rule would tell us that to calculate the derivative of the growth rate with respect to days, we need to calculate the derivative of g with respect to t for temperature, and we need to calculate the derivative of temperature with respect to d. So let's first calculate the derivative of t with respect to temperature. We haven't actually talked about how to compute the derivative when we've shifted both the period and the phase of the sine function as we have here. So let's go ahead and use that chain rule to help us out. Let's say that t of d actually equals t of f of d, and that f of d equals 2 pi over 365 times d minus 100. This allows us to write that t of f of d equals 8.3 times the sine of f of d plus 18.9. And using the chain rule, this is fairly easy to solve now. First, we can determine that df dd equals 2 pi over 365. Next, we can calculate that dt df equals 8.3 times the cosine of f, which is equal to 8.3 times the cosine of 2 pi over 365 times d minus 100. And now that we have both of these derivatives, we can use the chain rule to determine that the derivative of t of f of d equals the derivative of t with respect to f times the derivative of f with respect to d. And we can simply substitute in for each of these to find the derivative of t with respect to d, which is equal to 8.3 times the cosine of 2 pi over 365 times d minus 100, all times 2 pi over 365. Okay, let's clean things up a bit, but keep that derivative that we just calculated. And next we need to find what the derivative of g with respect to t is. That's actually pretty easy to do, because remember, g0 is just some constant. That's the growth rate of the bacteria at a temperature of 0 degrees Celsius. And Q10 is also a constant that determines the bacteria's growth response to changing temperature. And of course, the exponent up there is really just equal to 1 over 10 times t. So it's pretty easy to calculate the derivative of g with respect to t is equal to that constant out front times the constant in the exponent times Q10 to the t over 10. Now we just apply our chain rule to say that the derivative of the growth rate with respect to days equals dg dt times dt dd. Then we plug in the derivatives that we've already calculated, and we can figure out how the growth rate of the equali will vary in time. And we can use that information to help our bosses decide what the best course of action is to take with the tainted lettuce. It's a bit of work to go through those calculations, but really every step that we've taken was pretty easy. Okay, we just used the chain rule to learn something about how E. coli growth rates will vary throughout the year. Next, let's actually use the chain rule to derive another important rule for derivatives. Remember that before we figured out how to calculate the derivative of the sum of two functions, or the difference of two functions, or the product of two functions. But we didn't figure out any rules that we could use if we need to take the derivative of a function that is equal to one function divided by another function. So let's try that now. Specifically, let's ask the question, what's the derivative of f of x if f of x equals g of x divided by h of x? Well, first, let's remember that we can simply rewrite this as f of x equals g of x times 1 over h of x. And we can also remember that 1 divided by something is equal to that something raised to the negative 1 power, so we can rewrite this as f of x equals g of x times h of x to the negative 1. Okay, here's where the chain rule can be useful if we get sneaky. Let's define a new function. We'll call it j, and we'll say that j of t equals t to the negative 1. Well, after we've defined that new function, it's pretty clear that we can say that h of x to the negative 1 is really equal to j of h of x. And that means that f of x equals g of x times j of h of x. All right, now let's calculate the derivative of j of h of x. We know from our chain rule that it has to be equal to the derivative of j with respect to h multiplied by the derivative of h with respect to x. And since j of t equals 1 to the negative 1, we know that j of h equals h to the negative 1. So we can use our derivative of polynomials rule, which tells us that the derivative is equal to the exponent times the variable raised to 1 less than the previous exponent. So that means dj dh equals negative 1 times h to the negative 2, which equals negative 1 over h squared. And of course, h is a function of x, so we have h of x in there. And then the chain rule tells us that the derivative of j with respect to x is simply negative 1 divided by h squared times the derivative of h with respect to x. All right, now let's apply our product rule. If f of x equals g of x times j of x, then the derivative of f of x equals g of x times the derivative of j of x plus j of x times the derivative of g of x. We can now substitute in for dj dx and j of x, and we find that the derivative of f of x equals g of x times -1 over h of x squared times dh dx plus h of x to the -1 times dg dx. Okay, let me clean things up a bit, and then just slightly rearrange this equation. All we're doing here is moving the g of x to the numerator of a fraction, moving h of x to the denominator of a fraction, and then tossing in an h of x divided by h of x in there, which I did simply because now we have h of x squared in the bottom in both of the terms on either side of the plus sign. Next, we'll write it again, while just moving things around, to write a nice, compact equation. This is the quotient rule for derivatives. If f of x equals g of x, then then the derivative of f of x equals h of x times the derivative of g of x minus g of x times the derivative of h of x, all divided by h of x squared. This is one of those nice derivative rules that is important to remember. Although really, this shows that you could derive it yourself from the chain rule and the product rule if you had to. Okay, a couple more things I'd like to show you using the chain rule. Okay, we've got our chain rule up in the corner just so that you don't forget it. Now, in the last toolbox, we intuited that the derivative of the function f of t equals e to the lambda t was. But we didn't prove what it was. It's actually really easy to prove using the chain rule, however, so let's do that. First, we'll say that g of t equals lambda t times h of g, and h of g equals e to the g. Then we can easily compute their derivatives as dg dt equals lambda and dh dg equals e to the g. Next, we'll note that f of t must be equal to h of g of t, so df dt equals the derivative of h of g of t with respect to t, which equals dh dg times dg dt according to the chain rule, and we substitute in to see that this is equal to e to the g of t times lambda, and then we just substitute in for g of t and rearrange to find that the derivative of e to the lambda t is lambda times e to the lambda of t, which of course was the same thing that we concluded in the last toolbox. All right, now let's also look at f of t equals the sine of a t. This was another equation that we intuited a derivative for in the last toolbox. We can calculate it easily now in the exact same manner. We'll say that this time g of t equals a times t, and h of g equals sine of g, which means that dg dt equals a, and dh dg equals the cosine of g. Again, f of t equals h of g of t, so we can use the chain rule to show that df dt equals a times the cosine of at. Great. We easily proved these things that we had to assume in the last toolbox. For our last slide of this toolbox, let's really quickly just review all of these important derivative rules. I absolutely guarantee that you'll need to know these for the final, and that they'll be very useful to you if you decide to stay in science. Okay, the summation rule for derivatives tells us that if f of x equals g of x plus h of x, then the derivative of f of x equals the derivative of g of x plus the derivative of h of x. The product rule for derivatives tells us that if f of x equals g of x times h of x, then the derivative of f of x equals g of x times the derivative of h of x plus h of x times the derivative of g of x. The quotient rule tells us that if f of x equals g of x divided by h of x, then the derivative of f of x equals h of x times the derivative of g of x minus g of x times the derivative of h of x, all divided by h of x squared. And the chain rule tells us that if f of x equals g of h of x, then the derivative of f of x with respect to x equals the derivative of g with respect to h times the derivative of h with respect to x. That's it for this toolbox. Don't forget to take the quiz on Canvas.